Hello everybody, welcome to chapter 5.3, Gauss's method for adding numbers. Gauss's method for adding the numbers from 1 to 100. Gauss was a child when he discovered this method of adding together numbers. It was assigned as a class busy work problem to add all the digits from 1 to 100. So let's discuss this in a little more depth using the whiteboard. Add up the numbers, the digits 1 to 100. And what that meant is that he had to add 1 plus 2 plus 3 plus 4 plus 5 plus ... plus 99 plus 100. Or that's how one would think to do it. Now, if one did it the conventional way, let's just try to do 1 to 10. If one did it the conventional way, we would think 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And then you add, this would be 3, and then 6, and then 10, and then 15, and then 21, etc. But this would take a really long time if you tried to do that all the way up to 100. So what Gauss did, and we'll skip example number 1, and we'll go straight to Gauss's method. What Gauss did was take this problem, and that's what we're going to look at now. We're going to look at just adding 1 to 10 and what Gauss's clever method was. So we go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, just like one would think of it to be. So what Gauss did is Gauss saw, okay, that if I added the first and the last number, 1, 10, 1 plus 10, I got 11. And then if I continued on and I added 2 plus 9, I also got 11. And then if I went on and added 3 plus 8, I got 11. I got 11, and all the way through, so I'll go through the whole thing. Here we go. And then we have 4 plus 7, 4, 7, 4 plus 7 gives me 11. And then 5 plus 6, 5 plus 6 also gives me 11. So what he figured out, he looked at the number of pairs that we have. Each of these is a pair. So we see we have 5 pairs. So there are 5 pairs. And each of these pairs equals 11. So what he found, that if he multiplies 5 times 11, he will get the correct answer. So it turns out that the sum 5 times 11 is equal to 55, which would be the same as if we added it up the conventional way. So by looking at and then making these pairs, Gauss found a quick and easy way to add up the numbers. In example number 1, using a pencil and paper only, add up all the numbers from 1 to 30 and see how long it takes you to do this. Even though we skipped example 1 on the whiteboard, let us look at it here on the PowerPoint. So if we add up these numbers 1 to 30, it turns out that we get 465. And whatever method you use, if you use Gauss's method or you just add them up. But how did Gauss add up all these numbers from 1 to 100 instantaneously? He obviously could have done it the usual sequential way. That was what was discussed on the whiteboard, was how he actually did this. So reviewing what we just did on the whiteboard, in math it is often a good idea to examine a simpler situation first before trying to tackle a more difficult problem. So on the whiteboard we considered trying to add up the numbers from 1 to 10 in a non-sequential way. Can you see a possible method that might help speed things up? Clue 1. We circle the first and the last numbers. Clue 2, we circle the second and second to the last number. Clue 3, we circle the third and the third from the last number. We simply add together in pairs from either end. There are 5 pairs. Each adds up to 11. So we simply work out 5 times 11 is equal to 55. So the sum from 1 to 10 turned out to be 55, just like I did on the whiteboard. In example number 2, we're going to use Gauss's method to sum from 1 to 20. So let us go over to the whiteboard and work this one out. So we're going to use the same method to add up the numbers 1 to 20. So in order to do that, we do the same thing. 1 plus 2 plus 3 plus ... 18 plus 19 plus 20. So we want to see what the first and the last numbers add up to. So we have 20 plus 1 equals 21. And then we want to figure out how many pairs. Well, there are 2. A pair is made of 2 numbers. So this is one pair, and then this would be another pair and another pair. So the number of pairs would be equal to the number divided by 2. And in this case, it's 20 over 2, which means there are 10 pairs. So now, in order to add up those numbers, what we do is we say, okay, we take what the first and the last number add up to, and it's 21. And there are 20 pairs of these, so that will give us an answer of 210. So that's what the sum of adding up 1 to 20 would be. Reviewing what we just did on the whiteboard, we circled the first and the last numbers. Then we circle the second and the second to the last numbers, the third and the third to the last numbers, etc., to figure out how many pairs there are. And it turns out that there's a total of 10 pairs, and each of these pairs adds up to 21. So we multiply the number of pairs, that is 10 here, times 21, what each pair adds up to. So 10 times 21 gives us 210. And this means that the sum from 1 to 20 is 210. In example number 3, we're asked to add up all the numbers from 1 to 30. So let us go over to the whiteboard and work this one out. So we have 1 plus 2 plus 3 plus. So in this method, all we need to do is add up the first and the last and figure out the number of pairs. So in this case, we have 1 and 30. So 30 plus 1 is equal to 31. And the number of pairs, well, we see that that would be 30 divided by 2, which would be equal to 15. Therefore, we can just multiply them, so it would be 31 times 15 is equal to 465. We looked at this example earlier in example number 1, and I now showed you on the whiteboard using Gauss's method how to do this. Now let's just review on the PowerPoint here what we just learned in doing example number 3 on the whiteboard, which was the same as example number 1. So we circled the first and the last numbers, the second and the second to last numbers, etc., and found that there were 15 pairs totaling 31, because each of these pairs, when we added them, was 31, and there were 15 of them. So 15 times 31 gave us 365. Now, isn't that much easier than adding each one individually? So using Gauss's method, we found that the sum from 1 to 30 was 465. In example number 4, we're going to consider Gauss's task to add up all the numbers from 1 to 100 using his method. So let us go over to the whiteboard and do this one. Gauss's original task was to add up the numbers 1 to 100. And this is what Gauss did to his teacher's amazement. Took the first and the last and got 101. And then saw that 100 divided by 2, there are 50 pairs of these, meaning this is a pair, so there are 50 of them. And he took 101 times 50 and got 5,050. And if you check it on your calculator, you'll realize that's fine. So compared to what other students were doing and trying tediously to calculate it in the usual way, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus etc., he found a quick and easy way to calculate these. Reviewing what we just did on the whiteboard, we summed 1 to 100 using Gauss's method. We found that there were 50 pairs, each totaling of 101, so 50 times 101 is 5,050. And that is the sum from 1 to 100. This is a very easy calculation to perform mentally, since 50 times 100 is 5,000, and 50 plus 1 is 50, so when you add those two together, you get 50/50, or 5,050. In example number 5, we're asked to find the sums of 1 to 50 for A, 1 to 12 for B, 1 to 56 for C, 1 to 60 for D, 1 to 78 for E, and 1 to 200 for F. So why don't you try these on your own, and then I will work these out on the whiteboard. Okay, let's look at example 5. And under normal circumstances, I would have you work this out in class, but I'll work each of these out quickly for you to show you how Gauss's method works. So for the first one, we have 1 to 50, and that's A. So we add up. 1 plus 50 is 51. And we see 50 divided by 2 is equal to 25. Therefore, we have 25 pairs. So we have 51 times 25, and this gives us 1,275. For B, it's 1 to 12. So 1 plus blah, 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 plus 12. So we just have to do the first and the last here. So that will give us 13. And then 12 divided by 2 is 6. So there's 6 pairs. So it's 13 times 6. So that gives us 78. I hope you're seeing how much easier it is to add up these numbers using Gauss's method than just merely adding them as you go, as we would have thought of in the beginning. C, 1 plus dot 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 plus 56. 56 plus 1 is equal to 57. And then the number of pairs would be 56 divided by 2. So that will give us 28 pairs. So then we have 57 times 28. And that will give us 1,596. And then for D, we have 1 to 60. So when we add up the first and the last, we get 61. 60 over 2 gives us 30 pairs. So that means 61 times 30, and that will give us 1,830. For example, E, 1 plus 78. So we add 1, 78. So we have 78 plus 1 gives us 79. And then 78 divided by 2 will give us 39 pairs. And if we take 39 and multiply it by 79, this will give us 3,081. And then F, 1 to 200, so that will be 201. And then 100 divided by 2 for the number of pairs will give us 50 pairs. I mean, not 100, I mean 200 and 100 pairs. So there. So this is 200 divided by 2 is 100 pairs. So it would be the 201 times 100, and that's going to be equal to 20,100. On the whiteboard, we found that A is equal to 25 times 51, which is 1,275. B is equal to 6 times 13, which is equal to 78. C is equal to 28 times 57, which is 1,596. D is equal to 30 times 61, which is 1,830. E is equal to 39 times 79, which is equal to 3,081. And F is equal to 100 times 201, which is equal to 20,100. Gauss's method in general. How do we do this if there is a number without a pair? We could derive a formula that will speed things up even more. This will be the generalized formula for adding consecutive numbers. So why don't we go over to the whiteboard and I'll show you how to derive this formula. So what happens? So you may ask at this point, that's all fine, well and good when the number is even and that we have a pair and we can make a pair, but what happens when we don't have a pair? Like, for example, we have 1 plus 2 plus 3 plus 4 plus 5. So here's a pair. And then we have, here's a pair. And then we have, oh no, we can't pair 3 with anything. So we have a problem there. Well, this could actually be generalized. So it turns out what we can do is we can take, in general, 1 plus 2 plus 3 plus 4, dot, dot, dot. And we don't know what these are. So I'll put just question mark, plus n. But it turns out that the numbers before n, this will be n minus 1, and this one, that question mark will be n minus 1, and this question mark will be n minus 2, and the next one will be n minus 3, and so on until we get all the way back to 1. So what happens is that there's a way to generalize this. So we know that the pairs are n over 2. That will give us the pairs. And we know that we can add the n plus 1. The beginning and the end. So we have our number is n plus 1, beginning and end, and that we have n of these, n numbers. So what it turns out is that our formula would be n over 2 times n plus 1. So we just take our definition of the pairs times the number, and this will give us n plus 1 over 2. Now hopefully this number will start looking kind of familiar, or looks familiar from what we did in our last lesson, because it turns out that this is a triangular number. So what we did is we took the beginning and the last, 1 plus n, and then we had the number of pairs, n over 2, and then we multiplied them together, the pairs times the beginning and last, and we got the formula n times n plus 1. Let me write that a little bit better. So here we have, I'll just put the general formula up here. 1 plus 2 plus 3 plus dot 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 plus n minus 2 plus n minus 1 plus n, and I wrote 1 n, so that's n plus 1 will give us the number, and then again the number of pairs, n over 2, and then we take this n plus 1 and multiply it by n over 2, and this will give us our final answer. The sum will be equal to n times n plus 1 over 2. So that gives us the sum of it, of those numbers can be generalized to that. So here, the n, it doesn't matter what integer n is. So we don't have to worry about that problem. So this is the general formula for that. And if you notice that it looks just like our triangular formula that we did in the last lesson, as I just mentioned. Reviewing what I just did on the whiteboard, we have n consecutive numbers that we want to sum. And before n, we have n minus 1, and before n minus 1 is n minus 2. So we circle our pairs. If n is any positive integer, what is the number before n? What is the number before n minus 1? So the number before n was n minus 1, and the number before n minus 1 is n minus 2. So let's work out the formula like I did on the whiteboard, and we found that there was 1/2 n pairs, each totaling n plus 1. So 1/2 n times n plus 1 was equal to n times n plus 1 over 2. So the sum from 1 to n is equal to n times n plus 1 over 2. The method is easier than thinking about adding in pairs, particularly if n is odd, although it is exactly the same, really. We will use the formula to work out some problems without a calculator and look for further shortcuts. Note there is always going to be an even number on the top. So let's use this formula for 6 to find the sum from 1 to 15. So let's go over to the whiteboard and work this one out. So we'll write it down, the sum, our general formula. 1 to n is equal to n plus 1 over 2. And the first one here, we're asked to find the sum from 1 to 15. So we're going to find the sum from 1 to 15. So this little arrow here means 2, going from here to there. Well, we see that using our formula, well, what is n here? It turns out that n is equal to 15. So what we will plug in, so we will take 15 plus 1 divided by 2, and then I'll add up what's in there, 15, 16 over 2. I'll simplify it, and that will give me 15, and that will give me 15 times 8, and that which will give me 120. Reviewing what we just did on the whiteboard, we found that the sum from 1 to 15 is equal to 15 times 16 over 2 after we plug the number n is equal to 15 into the formula and did a little cancellation and got 8 times 15 is equal to 120. In number 7, we're asked to find the sum from 1 to 27. So we're going to use the formula to do this, and we'll go over to the whiteboard and work this one out. We are asked to find the sum from 1 to 27 using the formula. So again, we write our formula. This is the same as our triangular formula. And we're told that n is equal to 27. So now we do the same thing wherever we see n, we put 27. So it's 27 times 28 all over 2. And this is 14. So 27 times 14. And that will give us 378. Reviewing what we did on the whiteboard in example number 7, we plugged in n is equal to 27 into the formula to get this. We did a little bit of simplification or cancellation, and we got 14 times 27 is equal to 378. In example number 8, we're asked to find the sum from 1 to 87 using the formula. In example number 9, we're asked to find the sum from 1 to 100 using the formula. And in example number 10, we're asked to use the formula to find the sum from 1 to 93. So let us go over to the whiteboard and work these 3 examples out. The sum from 1 to 87 is equal to 87 times 88. 87 plus 1 is 88 over 2. 44. So that means we get 87 times 44. And that gives us 3,828. Then the next one, find the sum, what Gauss did, and we're going to verify that even the formula works here, which will be the sum from 1 to 100 is equal to, n is equal to 100. So 100 times 101 over 2, which is equal to 50 times 101. And 50 times 101 is 50, which is what we got earlier. And then the last one, the sum from 1 to 93 is equal to 93 times 94 divided by 2. 47, so that's equal to 93 times 47, and that's equal to 4,371. Okay, so that gives you an idea of how Gauss's method works, and so as you see, it's a much easier way if you're ever asked to add up the digits between from 1 to 100, now you know a quick and easy way to do it. Reviewing what we just did on the whiteboard for example number 8, to find the sum from 1 to 87, we plugged in 87 for n. We got 87 times 88 over 2, simplified it to 87 times 44 is equal to 3,828. In number 9, the sum from 1 to 100, we plugged in 100 for n and found that we got 100 times 101 divided by 2. Did a little bit of cancellation. We ended up with 50 times 101, which is equal to 5050, or 5,050, which is what we would expect because this was what Gauss had to do as a problem. In number 10, the sum from 1 to 93, we plugged in n is equal to 93, 93 times 94 over 2, simplified it, and got 93 times 47 is equal to 4,371. Thank you very much. I hope you enjoyed this video. Take care, stay well, and goodbye till the next time.